Disseminate, the computer science research podcast.
Hey folks, and welcome to another episode of Disseminate, the computer science research podcast. Today we're going to be talking about a paper from OOPSLA, which is my favorite acronym of all the conferences, by the way. That stands for those who don't know. It stands for Object-Oriented Programming Systems, Languages, and Applications. And the specific paper we're going to be talking about is validating SMT solvers for correction and performance via grammar-based enumeration. Now, this paper was written by Dominik Winterer and his colleague Zhengdong Su, and I'm really happy to say I've got Dominik with me today on the podcast. So welcome, Dominik.
Thank you, Jack, for the nice introduction.
Cool. So yeah, I guess we'll go into your journey in a second, Dominik. But you're going to be you finished your PhD and your postdoc, and you're going to be an incoming lecturer at the University of Manchester in September, right? And you're hiring, right? So we can get this plugging straight away as well. So to any listeners who are interested in formal methods and whatnot, do reach out to Dominik. But yeah, cool. So welcome to the show, and it's always customary on the podcast for the guests to start off telling us about their story. So yeah, tell us about your background and how you became interested in formal methods and your research area.
Yeah, basically, I grew up around computers in the early 2000s. And so that sparked a great interest when my father was building a computer inside our living room. And then I started doing my studies in the University of Freiburg in Germany, which is a beautiful and enjoyable place. And there, logic and math and these things were really the focus. And in order to pass a computer science degree, you had to master these things. And during this time, I also learned a lot of several amazing mentors that taught me research and wanted to me get interested in their research on symbolic AI, where Freiburg at the time was still a big player and a great place to be. And so the pivotal moment, essentially, which struck or which tied me to research career was essentially when I saw a research lab come together in front of a deadline. The kind of energy that was there was really amazing, and that really started everything. Did a research internship at the IBM in the US, and then, as you said, I did my PhD at ETH Zurich and postdoc, and now I'm happy to join the University of Manchester in September.
That's fantastic. Yeah, so I know you said there in that Freiburg's a beautiful place, and that's the one right on the edge of the Black Forest, right, or around there, that part of the world, right?
That's right.
Yeah. I remember going there as a kid, and I really loved it. Beautiful part of the world. Cool. So yeah, and obviously Manchester next, that's going to be fantastic as well, and sort of building your own lab, right, and sort of fleshing that out, and that maybe, so I guess some of the experience you mentioned there that was inspiring. I guess you're going to try and put that into practice again on your own path, right? So that's really cool, and I hope that goes well for you. So next, I guess let's ground ourselves for this chat today and set some background and some context and some of the key terms. So yeah, I guess, I mean, for the uninitiated, what are SMT solvers and what's a grammar? And tell us about all these key words we're going to need to understand for this chat today, Dominik.
Yeah, I may add to the previous question maybe that I got interested in this formal methods software engineering world by combining essentially what I had in Freiburg, which was formal methods, symbolic AI research, which is kind of similar. And when I got to ETH, a very practical software engineering, and I built those two, I merged, and that's how I got interested in SMT solvers, essentially. SMT solvers are, you can think of powerful theorem provers that take formulas and decide whether these formulas are satisfiable. That means whether they have there's an assignment to the variables in the formulas, or whether they are unsatisfiable. And so these SMT solvers are nowadays used as a critical infrastructure for software research and industry, specifically in testing and verification, for example, and so symbolic execution, or also for verification of whatever is necessary to verify. And so these are SMT solvers. SMT solvers are complex pieces of software. They have a lot of logic and intricate algorithms inside of them. They solve NP-hard problems, and they are very important for software industry and research. And so, yeah, maybe a bit of background on grammars. All you need to know is pretty much Computer Science 101. Context-free grammar is essentially very, very much represented as you would write it down on a paper. It's similar in a file. But they are used for what I also should give some background of is a black box testing, which is the goal is to create as many test inputs for a particular software to fire at, and take using these inputs we want to find bugs. And grammar-based testing is we use a grammar to describe the inputs that we want to generate and throw it at a software under test, essentially.
Okay, cool. Yeah. So, sorry, Dominik. Continue, please.
Yeah, I just wanted to add that we aim to test SMT solvers in that case.
Cool. Yeah. So you mentioned there, like fuzz testing is sort of a traditional way of testing these types of solvers or these solvers. So what are the limitations of those approaches, and that sort of make the grammar-based approach to be like more advantageous?
So you can think of the different ways of there's several ways of testing. You can do mutations on existing inputs, or you can basically let the inputs describe the inputs from the ground up, which you can do by grammar-based. So with grammar-based, I wouldn't say that one is superior to the other. It's more that they are orthogonal. And we use grammar-based testers in this case because we wanted to enumerate inputs from the ground up, from smallest to large inputs.
Okay, cool. That's sort of a nice segue then into the kind of the elevator pitch of the paper and the motivation of the paper then. So yeah, what was the overarching kind of goal of the paper, or maybe there's some sub goals in there as well? Yeah. So
the overarching goal of the paper was to because at the time SMT solvers were tested quite a lot, and there were several fuzzing campaigns have been done, and many bugs have been found, and many fixes have been done by the developers. But all these SMT solver testers were unsystematic, or essentially random based. And with random based fuzzers, it's unclear when to stop. Usually the bugs that they trigger were very sizable, such that you need a lot of time to reduce these bug triggers to a size where developers can even think about triaging these bugs. And so with all these testers and all these bugs, it wasn't also not quite clear whether SMT solvers do even become better over time. Although there was like a big academic effort to find more and more bugs in SMT solvers. And so the motivation for us was to try and like, first of all, twofold. Make it very simple. Try to find the most simplest bugs that are not causing too much trouble on the developer's side. So we want super small formulas, and we also want to, with these super small formulas, we want to judge the evolution of SMT solvers. And we can do that because we have done an evaluation before on and found that 85% of all bug triggers in SMT solver are indeed reduced to small bugs. So we're quite confident that we find a lot of important bugs with this method.
Yeah, that's cool. And I really like the sort of the goal of sort of trying to evaluate this sort of correctness and performance over time. It's always a really nice aspect of, or a really nice goal to have. So let's get into how you went about achieving these goals then. So walk us through the sort of the design of the key components, and the thing you designed is called ET, right? So we need to know why it's called ET as well at some point as well. And yeah, tell us about how you went about designing ET and what the key components were.
Yeah, so maybe first on the name. ET should be shortened on for enumerative or exhaustive tester, or also extraterrestrial, because when we were initially finding the first bugs with this tool, was quite magical that they were super small and we did not have to do anything to reduce them further. We could just give them away to developers. How ET works is pretty simple. It takes we formulate context-free grammars for the different SMT theories. We have grammars for the core theory, is essentially Boolean logic. Then we have for arithmetic, strings, and so on. And then we compile these grammars into algebraic data types in Haskell. And then we use an off-the-shelf tester called feed that can then enumerate the inputs. So it's more about the insight of finding small bugs rather than the technology or the key idea. So in a sense, the real contribution here is really to keep the bug small and investigate evolution rather than making a technical or conceptual approach contribution.
Yeah, just for the uninitiated here, Dominik, when you say sort of a small bug versus a large bug, what could you give us a concrete example of that, and like what you actually mean there by the difference between small and large?
Yeah, so essentially what I was talking about or was referring to as bug is not quite a bug. It's a bug trigger. It's an input that can manifest a bug in a software. If that input is very large in size, which means, for example, in the SMT, it means like a nested formula with lots of variables, lots of nested components. That's difficult for the developers to find out why this formula triggered a bug and what the root cause of it is. And if you, on the contrary, you have a very small bug trigger, it's minimal even, then you cannot, you have essentially, you can at least think about which of the components that you see in the input could be causal for the root or could cause this bug, and which is basically which makes a difference whether developers can even look at bugs or not. Like if they're small enough, they might just straight out reject too large bugs.
Yeah. Okay. Cool. I get it. So I guess when you were building the sort of the ET pipeline and these various different steps in there, you said that you grabbed kind of an off the shelf tool for doing the enumeration. What made you choose that specific tool? I think it's called Feet, right?
Right.
What was the reasons for choosing that versus something else, or is that not really too important in the overall pipeline? You just basically needed something to enumerate.
Yeah, I needed something to enumerate for sure. And initially, I was building this tool myself, and essentially used a search procedure. But then I discovered this tool Feed, which is just faster, and I just replaced that component which I've previously designed myself. But overall, I think the key that I wanted to discover is whether I can judge the evolution of SMT solvers with this approach.
Cool. So let's talk about the results then and what you found then. So first of all, walk us through how you go about actually evaluating something like ET. Like, what's the setup like? How are you actually going about to prove your research questions?
Yeah. So there are essentially two aspects here. Like ET is a powerful testing tool, and it's a way to judge the evolution of SMT solvers. The first, for the first goal, we essentially try to do it in a traditional way. Try to find do a bug hunting campaign and find bugs in SMT solvers. Essentially, bugs that were not found before. For the and we found 100 bugs, and most of them got fixed. And for the second part, which I was very excited about, or am still super excited about the evolution, we essentially looked at all SMT solvers, all SMT solver releases from the last 6 years, and stacked them up. And then we ran these different grammars on each of them representing a different SMT theory. And by that, because we cover all 8 SMT theories, at least the official ones, this gave us a way of approximating the evolution over time, essentially. How, for example, we found that in old versions of SMT solvers, there were many bugs triggered, while the number of bugs and unique bugs went down as the versions got more recent. So that was quite stunning to see that we could even see that the fuzzing campaigns that have been conducted by other tools have affected this, or have basically caused part of this downward curve to the new releases. So indeed, we could, at least in part, validate that the fuzzing has benefited the SMT solvers.
Yeah, that's really cool. So let's focus on the results some more then. So you kind of headlined it there that you found over 100 bugs. What was the breakdown there between sort of correctness and performance?
So we essentially found quite a few correctness bugs, and so many soundness bugs essentially, and also performance bugs. So was pretty much half. So we found half of the bugs that we found are correctness bugs, and the other half is performance bugs. That said, this tool is the first one that has enabled us to even file these performance bugs, because as I mentioned earlier, it's very hard to triage bugs in such complicated systems when the triggers are large. But it's almost impossible to do that for performance bugs, because then you don't have a way to actually differentiate. When you have a crash or something, you can easily reduce the trigger to something that's smaller, because there are tools for that. But if you have like a timeout, each time you shrink down your initial bug trigger, you again have to wait to see whether the timeout happens, and so it's not easy to shrink down triggers. That makes it even the more important that these performance bugs have small triggers, and ET is, in my opinion, the first tool that can even do this, and that's why we could use it to file performance bugs in SMT solvers.
Yeah, it's really cool. Of the bugs that you found, Dominik, what was there any of them that were sort of really surprising, and which one maybe has had the most like impact, I guess? In fact, like, you uncovered something quite not scary, but though I'm not sure what the quite word I'm looking for is. Like, that was really surprising, and that could have been a really critical issue for something.
That's difficult to pin down. So we found quite a few soundness issues, each of which could cause something like a false verified program if it's hitting that particular bug. So it's hard to say. Of these soundness bugs we found, I think it was about 13, and there were quite a few stunning ones. I think that out of these soundness bugs, what impressed me the most is that the triggers were super small. Essentially, you see a quite critical bug in SMT solvers that's super small, which you thought would have been detected earlier, maybe even by the regression test suite, but wasn't. And so that was a bit of a shock to see these small bugs that appear.
Yeah, you often wonder like how if they've had any sort of real world knock-on effects, right? Like they've been lurking in there for a while, and they might have they could be the cause of something. But yeah, it's amazing that exists now, and that they've finally sort of been Cool. And what's the proportion of ones that have been fixed? Did you say? Sorry, I missed that.
The proportion of the fixed ones is probably it's larger now, but it was at the time it was 40%. It's probably more like 70 now.
Yeah.
So yeah, so the average of all the SMT solver bugs that I have ever filed is something like 80% of them get fixed.
That's pretty good. What's the process like for getting them fixed? Is it how? I mean, do you ever go in there and fix them yourself? You're like, I've got to go and fix this damn thing.
I should actually do that. I have filed way too many bugs in SMT solvers. Yeah, that's why I haven't fixed bugs in SMT solver. I should go ahead and do that. Cool. But in general, we try to we try to shrink the bugs down as much as possible. Then we file these bugs, and we also try to not file duplicate bugs, because that would just cause too much issues to developers.
Another point you mentioned a second ago is that you can kind of see the over time this sort of downward trend, and that the fuzzing campaigns have actually had some positive impacts, and you can see this. Were there any cases of regressions between versions popping up where you kind of the overall trend was down, but between version 5 and 6 there was actually an increase?
Yeah, we have seen this quite a bit. Like in Z3, so we tested two solver families, Z3 and CVC5, which are the two biggest SMT solvers. In Z3, we haven't seen that very much, except for one theory. But for CVC4 or 5, we saw that, because there was a big version shift from CVC4 to CVC5, where they essentially re-engineered the tool completely. And so this caused bugs in 2 or 3 theories out of 8. So we could see these issues both in terms of correctness and also in terms of performance bugs.
Yeah, that's really interesting to see that we don't write bug-free code.
No, we don't.
Cool. So, looking forward to the future now, how does ET evolve in the future to find more bugs in these? And I'm guessing there must be more bugs in there, right? So yeah, how do we go about realizing that? And so what does the evolution look like of this direction of research going forward?
Yeah, I guess one crucial thing we are working on at the moment is to extend the evolution analysis to more solvers beside the two big ones, because there are more than a dozen SMT solvers, and we need to know the evolution of each of them. And on top of that, what would be super important is to go beyond academic bug hunting campaigns. Or what do I mean by that? Essentially, we need something like continuous integration of fuzzing pipelines for SMT solvers, because currently, essentially, it's the case. Once somebody wants to write a paper, has identified an approach that finds bugs effectively in SMT solvers or other tools, then spends time and compute, finds these bugs, files them, get them fixed, and writes the paper, and essentially publishes the tool on GitHub, and that's it, right? But what we need instead is something like continuous integration, that we effectively integrate these fuzzers in a continuous integration pipeline, and so find bugs continuously. So that's a second point.
Sure, yeah. On that, so the sort of the main SMT solvers like Z3, they're open source projects, right? And so how are they actually managed? So they basically you need a way to sort of get things like ET into their pipelines essentially. And did they do that at the moment? As you've had any communication with the developers of that project and sort of how you can get your stuff in there, so it is running continuously and is finding bugs as they're developing, rather than waiting for them to release a version, then you can test it.
Yeah, but I think the integration of this is also not necessarily straightforward, right? Because there are some questions there. For example, when should we stop? Like with ET here, we have as a research effort, I just let ET generate a lot of test cases, 1 million per theory, and so that makes 8 million if you have 8 theories, and that's not feasible for a CI at the moment. So we have to do something smarter. We might need to work with coverage to reduce the number of test cases that you have to run. Another problem that ET currently has is the fact that it sometimes creates alpha equivalent inputs, essentially just with different same formulas with different variable names. And we also have want to tackle this issue.
Cool. Yeah. Are you got any plans of sort of adapting ET to sort of maybe other domains as well outside SMT solvers?
Yeah, we already found some issues in JavaScript engines with it, but it's work in progress, and it's basically connected to the idea of making it alpha or reducing some of the alpha equivalent the programs, but ET can be adjusted or applied to anything that has a context-free grammar. So essentially, it has a lot of, like there's these big Antler repositories where you have lots and lots of grammars for different tools. You can use ET out of the box and use these grammars. I think one caveat there is you have to limit the number of variables. Currently, for formulas, we use 2, and yeah, we also have to fix the number of constants. Otherwise, right, if we don't, then the enumeration would just go enumerate the integers or something.
Cool. Yeah. The next section of the podcast, I want to focus on sort of impact. We touched on it slightly a second ago about kind of you want to see it being integrated into sort of CI pipelines more and things like that. But kind of with ET and obviously your wider work in this area, what impact do you think it can have on the community and on industry as well?
Oh, that's a big question. I mean, I hope the underlying vision of the research, or the underlying vision of my research specifically, is to do something like formal methods engineering. Formal methods engineering should be a discipline between formal methods and software engineering. And what we want to do essentially there is we want to make sure formal methods tools are correct and reliable, because the promise of formal methods tools is to make software reliable. And if these tools are not reliable themselves, that's not that's not a trustworthy endeavor itself. So that's one prerequisite. And the second is to be able and combine formal methods, because currently they are often used in isolation. There's other problems like there's so many different formal methods out there with lots of different specification languages which have overlaps and all that. And I hope to make a contribution to consolidating some of these as well. And of course, like the third big challenge I see is the specification crisis. Essentially, that we still write software largely without specifications, and so I also want to make a contribution towards that, such that we have better tools that incentivize people to write as specifications. And why do we need this? In order to apply these techniques from methods tools which need specifications. Otherwise, it's not possible to verify or even test something.
Yeah, I definitely agree with you. You kind of the guarantee with formal methods like this is if this says that it's correct, is that yeah, it's actually correct, right? So you kind of want if you don't have that guarantee, then sort of it undermines confidence in those tools, right? So it's super important. I agree with that principle, and the other ones you mentioned there as well. I'm going to ask you. The next question I'm going to ask is a bit off topic, but it's only because I was on a panel yesterday for databases and the role of databases in AI. And AI is everywhere at the minute, Dominik, right? Everyone's talking, right? So unfortunately, I'm going to have to ask you the question of what are the implications for the new wave of Gen AI and AI and everything? What are there any effects of that on the formal methods community? And are there any things that we can learn from that, or from formal methods engineering, this sort of the idea of combining these two disciplines can that be applied to the AI domain as well? Because obviously having confidence in the output of some of these LLMs and stuff like that it's hard to have confidence in them. So I don't know if there's lessons that can be learned between from one community to the other.
Yeah, there's definitely lots of lessons that might be learned from that. Although I cannot specifically comment on like the big picture, because if I could, then the whole problem would be resolved, and we could just trust our ChatGPT or whatever language model one uses. But I think one particular interesting aspect related to formal methods engineering would be to have something like software validation portfolios, where which take a prompt, a natural language prompt, and then apply whatever possible software validation technique. Could be testing, could be verification, could be whatever it is, and then as an output give some sort of either provide bugs, or if there's no bugs, provide some certificate for the rigor of the methods that have been applied. So that would be like a grand vision, to use part of this AI, mostly language related, LLM related AI as a front end to a verification back end.
Yeah, I can see that being really useful. Yeah, that'd be a nice, interesting crossover between the two. I now want to sort of change gears a little bit. We spoke about surprises across the chat a little bit, but whilst there's going to be two questions here, Dominik. So the first one is going to be just localized to ET, and I said, like, whilst working on the ET project, what's been the biggest surprise? And then I want to take that question and then expand that to the sort of the wider field of formal methods, and sort of get your take on both. And what's been your biggest thing of like, oh my God, I did not expect this. Caught me totally off guard.
Yeah, I guess one of the biggest surprises was indeed that I could find so many small bugs in SMT solvers still after all these years of testing. And the other big surprise was that indeed it's possible to see some evolution. And it's even, I was shocked to see that I mean, I shouldn't be shocked, but I was shocked to see that there's a clear-cut correlation between where the fuzzing campaign started and where the bugs went down. I wasn't expecting to see that in the evolution plot. So those were the two biggest surprises, I should say.
Yeah, and like visually to kind of just look at it, but you must be thinking, oh my God, this just maps perfectly. Yeah, that must have been a really nice experience. Yeah, and I guess so. Yeah, some question B of this question for the wider field, then I guess as well, in your wider time in research.
Yeah, so for the wider time in research, of course, right, I probably will refer to the time that I spent in my PhD, which I was always like fascinated by these proving tools such as SAS solvers, SMT solvers, or optimization solvers, and was playing around with these three in particular, which I fell in love. And so one thing I did when I essentially arrived in the new lab, I found a colleague of mine was testing SAT solvers, and we were kind of surprised how reliable these tools are. Like there was very, very little bugs we could find, even though we would throw millions of test inputs at these tools. And then we came up with the idea of testing SMT solvers, and we weren't taking it too seriously. And then we applied one of our methods to SMT solvers, and we were surprised that we could actually find soundness issues in SMT solvers automatically. So that was a really big eureka effect, I would say. It's probably the biggest one I had in my research career, when there was like essentially this tool spitting out a soundness issue in Z3, and we were validating it. We were basically super excited and and shouting around, shouting in the hall of ETH, which has this old former chemistry building, and so that was really really crazy, I should say, that indeed we could find bugs in SMT solvers, which before was not clear. There were just a few soundness bugs that were found by applications for the most part, but the fact that we could find them automatically and then we could find so many more, that was really, really exciting.
Yeah, I bet that must have been a great experience. That's what it's all about, right? We all want those sort of eureka moments. That's sort of that's what it's all about. That's what it's all about. So yeah, that's really cool. So I guess now we've spoke about ET and whatnot. It'd be interesting to hear about some of the other research you've got going on as well, and sort of to dig deeper into the vision you have for your new lab at the University of Manchester as well. So yeah, tell us about the other stuff, the other cool stuff I know you're working on, Dominik.
Yeah, so I think it's a bit unusual, but I have most of my research is centered about testing these SMT solvers. I've devoted, for the most part, my entire PhD on attacking this one problem. And now I'm trying to, instead of just finding bugs in SMT solvers, I'm also trying to make SMT solvers better, in the sense that I want to design approaches how we can bypass bugs, right? Because there's always there's always a lot of bugs, and we cannot, at least at the moment, we cannot produce like large scale verified systems, right? And so one thing I kind of take advantage of, or one thought that really caught my attention is we can use instability in big software to our advantage. So essentially what we can do with something like an SMT solver or compiler, we can massage the input in equivalent ways, such that we have lots and lots of different equivalent inputs, and then process these let these inputs process in the tools in parallel. So the idea is is a bit similar to n version programming, but it's not like that we have n versions of the software, but we have n versions of the input to the software, and essentially then use an oracle at the output to decide which output we take. And I found that like this instability, like changing, because like instability is currently a big issue in the formal methods community. Because if imagine if there's a change to an SMT solver, it could prove some fancy proof yesterday, but now there was like a commit that changed a little bit of logic in SMT solver. It no longer can prove the same theorem. So that issue can be, I would claim, can be partially tackled by parallelism and this, basically turning the testing idea around. Like instead of producing these equivalent or different inputs to trigger bugs, we essentially correct the software by that. So that's the current thought I am a bit addicted to at the moment.
That's really cool. Yeah, that's a very nice segue into sort of, I guess, my penultimate question for you, Dominik, and that is how you actually go about arriving at that point, right, and having this sort of creative inspiration and the creative process. And so do you have a systematic way of attacking the creativity and generating ideas, and then obviously once you've generated those, saying this is the one that's gonna, be the one for me, worth pursuing for a significant amount of time?
Oh, that's a great question. I love to talk about with people all the time, because I have thought about this a lot, how to develop, but I don't actually, I don't have such a systematic way. I would love to, but I don't have that. So unfortunately, these eureka moments or these insight moments are quite rare. And this one on instability I had when I was basically under extreme pressure in front of my PhD defense. So the night before, or the day before, essentially my advisor told me that my presentation is a bit off. And then I had to redo a bunch of things. And so when I was done, essentially, once I was done, I thought, okay, what else should I do? Because of the script changed a little bit. And so I thought, what is the meanest questions people could ask about this research? And so I came up with the question, why essentially is this all useful? Why would you even spend so much time to find all these bugs when indeed what you could just do, you just reformulate n versions of the input formula, use a bit of more compute or substantially more, because nowadays, like, at least workstations have hundreds of cores. Use those cores, and then who cares about the bugs, right? If you find one particular input that where the solver produces correct result, then just take that. And so essentially that was an answer to this very mean question.
Yeah, that's a really interesting way to approach it, right? Sort of flip it on its head and sort of look at it from, I guess it's almost like putting yourself in somebody else's shoes in that sense, and then thinking of sort of the possible ways they can ask you that, and yeah, no, that's a really interesting way to sort of tackle it, and a nice heuristic or a nice tool in the toolkit for thinking about a problem. That's a nice.
But it was not deliberate at all, right? It was totally accidental, right?
It was like kind of almost
as a rehearsal for the actual defense the next day, right? So it wasn't.
Yeah. But it's cool that you kind of learned that and you kind of had that observation now. And I wonder if it has the same sort of efficacy, if you sort of are doing it not under pressure. You probably brain isn't working quite a different way. Maybe you need the pressure element as well for it to work. I don't know.
I think at least I do. Yeah.
Cool. Yeah. Well, we're arrived at time for the last word now, and so yeah, what's the one thing you want the listener to leave this podcast episode with today? The one takeaway.
Yeah, I think the one takeaway is essentially I want to have people embrace the idea of combining or at least bridging the gap between software engineering and formal methods. And in that sense, we need something like formal methods. So my claim is we need something like formal methods engineering, which takes the nice aspects of the software engineering community and applies it to formal methods. It systematizes formal methods, makes the tools better, pragmatic approaches how to combine the tools, consolidate them, and so on. So essentially, it's a call for formal methods researchers to publish more of their work in software engineering venues, where people like me certainly would appreciate it.
Yeah, there's a good call to action there. And at the Seminate, we're also a big fan of bridging the gap. So nice use of that phrase as well. So yeah, that's fantastic, Dominik. Thank you very much. It's been an absolute pleasure to talk with you today. Any of the relevant materials we've mentioned, we'll drop links in the show notes as well. And so people can we'll put you. Are you on social media, Dominik, anywhere? Are you on the?
Yeah, all over the place essentially. Yeah.
Okay, cool. We'll link those in the show notes as well. And yeah, thank you very much. It's been a lovely chat.
Yeah, thank you, Jack.
Cool.
Very appreciated.
Cool. And we'll see you all next time for some more awesome computer science research.